So my talk today would be about Azure Machine Learning, but in particular about how we can use the machine learning capabilities of Azure Cloud to do something useful with COVID-19 paper corpus. I'm actually very excited that there are two talks today on how AI and machine learning can actually improve the situation with COVID-19. And I'm looking forward to the next one as well. So the thing that I'm going to talk about is the NLP, and the problem is that there are a lot of scientific papers being published on COVID-19, about 30,000 per month, and this number is growing. But luckily, all of them are collected in one beautiful data set called COVID-19, which now contains over 800,000 papers on the subject. Half of them are with full text, half of them are with abstracts and just the metadata. And it's interesting to see what we can do with this data set, having the tools of NLP with us. A human being cannot possibly process this large volume of information, so we want to create some kind of tool that will on one hand help the scientists in the area of biology and medicine to somehow navigate this data set, and secondly to extract somehow some knowledge and insights from that. And the way we can do that, I mean, there are several things that NLP can do for us. There are simple tasks like classification, but things we are particularly interested in is named entity recognition, because if we are able to spot entities in the paper, then we can somehow get the idea of what this text is about. Recently, there's been a lot of progress in natural language processing with the appearance of so-called language models, such as BERT, GPT, and so on. And the idea is that text is such a nice data to work with, because there is a lot of text available around. And we can take like the whole text available on the internet and in the collections, and use it to pre-train neural network to get the sense of how the language works. And then on top of that, we can train model to do some more specific tasks. So we will be basing our project on BERT. So the idea of BERT is the following. It's a so-called masked language model. So we take the text and we train the model to predict some missing words. So some of the words in the sentence are masked, and the model has to predict them. And by doing so, it learns the structure of the language. BERT is a huge model, so we cannot train it from scratch, and we need some kind of pre-trained language model to do that. So the idea of the project, like to give the overview of what we have been doing, is the following. We can start with the corpus of scientific papers, and then we try to extract entities and relations from that, and store them somehow in the JSON data store. In Azure, there is a database called Cosmos DB, which is good for that. So we will use Cosmos DB, from which we can then do querying on entities and relations. And this can be done in SQL. This can be done using some visual tools such as Power BI. And also we can do some further data processing to extract some insights and draw some graphical infographics. So first of all, the first part is extracting entities. And to do that, we need to train our model. And for that, we need a data set. We've been looking for a good data set to do that. It turns out there are a few publicly available data sets. One of them is specific for coronavirus, which is called Medical NER, available on Kaggle. But it is very small, like only 300 entities and about 40 scientific papers. The goal of this data set was exactly what we are going to do, to extract meaning from scientific papers, but unfortunately the data set is too small. There is also the data set called BC5CDR, which is larger, but it only contains a few entities such as disease and chemicals, and it is not COVID specific, so there are no specific terms for COVID-19. So that is one problem that we were facing. The second problem is like what base language model to use, because if we use generic BERT, that does not give us sufficiently good results because it's not specialized for medical terms. Medical terms such as hydroxychloroquine um, requires some special treatment, because even tokenizing them is tricky. Because if we tokenize them as one token, that's probably not the best idea. We can, if we tokenize them in parts, then we can extract some meanings from parts of the words. So that is what we should probably be doing if we want to process medical texts. So luckily, so the ideal thing would be to pre-train the BERT on medical text, but luckily Microsoft Research has already done it for us, and we were able to use the pre-trained model. So the BC5CDR dataset for entity extraction looks like this. It contains title and abstract of the paper, and then marked up entities, which looks like this. So the position in the text and the entity itself, and then the type of the entity and mapping to some medical ontology like UMLS, which is really good. To train the classification model, normally NER problem is considered to be token classification model. So we split the text into tokens using tokenizer, and then for each token we map corresponding entity. But we also distinguish between the beginning of an entity and the inner part of an entity, and that is required because if we want, for example, two entities next to each other, we want to distinguish between them. So that's why we need two tokens for each entity. This is so-called IOB classification. So as I mentioned, Microsoft Research has released the model called PubMedBert, which is the BERT model pre-trained on PubMed, on the database of medical papers. And it is available as already existing model in Hugging Face library. Hugging Face transformers is de facto standard for NLP tasks, and we've been using that. So using this model is as simple as loading it by name. So essentially what we do, we instantiate the model, give it the number of classes, and then we run the trainer to train it. So that is the first thing we did, and we did it using Azure Machine Learning. So to give you context, Azure Machine Learning is the tool for data scientists, both for beginners and for really experienced data scientists. It started as the internal Microsoft product, and then it evolved into something more complex. There are some tools, as I mentioned, like Designer and Automated ML, which can be used with people with really small machine learning experience. But it can also do things like scheduling experiments on the cluster, hyperparameter optimization, and simplifies those things a lot. So normally when you work in Azure Machine Learning, I will show you briefly how it works. So Azure Machine Learning has this portal online where everything is collected. Like the main notion is called the workspace. And the workspace is where you have everything. You have data, you have clusters, you have pipelines, notebooks, and so on. And you can see those elements are here in the menu on the left. And because it's a collection of those tools, there is no one best recommended way to use Azure Machine Learning. And that is a little bit confusing, because normally you would probably expect, like, a tool like here you upload your data, then you run experiments, and then here is your result. And that is more complicated than that, because there are many things you might want to be doing with Azure Machine Learning. And the simplest thing and the good thing to start for a data scientist is just to run notebooks. Like if you go to notebooks, you will see familiar Jupyter notebooks. Yeah, I'm getting comments that the slides are not really good. Yeah, unfortunately, I will not be able to show you the demonstration today. So the idea, I was speaking about Azure Machine Learning. Azure Machine Learning contains the collection of tools, and normally you would start by just running a notebook. And the advantage of using Azure Machine Learning comparing to, for example, a virtual machine in the cloud would be that in Azure ML, notebooks are decoupled from underlying compute. So what you can do, you can start working on the non-powerful machine with the CPU. And while you are doing data processing, while you are figuring out the format of the data, and once you are ready to start training the model, you switch to the GPU-based compute, and you don't have to move any data because you just change the compute. The data stays in the same place. And what you would also probably want to do to use the dataset feature in Azure ML to put all the data in a dataset, and then this dataset would be easily mountable to any compute. Which is a good thing because once you are done with the notebook, you might want to switch to the cluster for training. And the good reason to do that is when you want to do repeatable experiments. Because in the notebook, everything is manual. But once you have the script for training your model ready, you can export it to a Python script and move to the automated training using cluster. And there are a few ways you can do that. You can do that from Azure portal through the web interface, which is not very convenient because it's not repeatable. And the best thing which we recommend now is using YAML files to describe everything, to describe all data sets, experiments, and so on. So what you would do if you want to train this model on the cluster, you would describe the data set. So if we can move to a few slides forward, and one more, this one. So you can describe the data set as the YAML file, pretty much like, here is my file. I want this to be my data set, and then you run the command to upload it to the cloud. Then if you want to train on the cluster, you need to specify the environment on which it will run. And environment is pretty much a container. So you can say, I want to start with this container, and I want to apply a certain conda configuration. And there you describe like which conda packages you want to install, which pip packages you want to install, and you create this environment. Environment pretty much is equivalent for container. And then next slide, please. And then you describe the experiment, like which script do you want to run, which environment, which compute. And compute can be like GPU compute, CPU compute. You can create a compute either from command line or through the portal. And then you just submit your job. And once you do that, the experiment will run. The way it will happen is that Azure Machine Learning packages current directory, submits it to the cluster, runs the script, collects the data. And you can log any metrics within the experiment. And you can also log like any binary data. So for example, once you train the model, you might want to save it to a certain directory, and it will be automatically captured as part of the experiment. So by doing so, you have the really repeatable experimentation. You don't have to worry about losing the results, about forgetting what the result of the experiment was, which is good. And once you do that, you can train the model, and you can see that this model produces reasonably good results. So we started with this experiment. What you can also do, which I haven't mentioned right now, is to do hyperparameter optimization. You can say, for example, I want to run this experiment with different parameters. I want to sample those parameters from certain distribution, like for example from 1 to 100 with uniform distribution. And it will automatically schedule the number of experiments. You can say, I want to like run for 3 hours and schedule experiments until I get reasonably good metric. So that all that can be done using Azure Machine Learning. So that was our first experiment. We got reasonably good quality, but not good enough. And around that time, Microsoft released a service called Text Analytics for Health. And Text Analytics for Health is based on PubMedBert. So it's essentially the same kind of direction that we were going. But it is the service the fully trained end-to-end service, which you can use just by calling the Cloud API or by using the containerized API. And what it can do, if you can switch to the next slide, please, it can do entity extraction, mapping of those entities to medical ontologies, and also it can extract relations. That's the next slide. So you can say, for example, we have certain symptom or sign, and that sign occurred at that specific time. So all that relations can be extracted from the text. So now to use that, you can switch to the next one. We can use the Python SDK. So Python SDK pretty much allows you to call one function and have all the entities and relations returned. The next slide. And that is how the result looks. And next one. So what we now needed to do, we wanted to analyze, to begin with analyzing all abstracts in the core data set. And because this data set is large, it's pretty large, we figured out that we need to parallelize the process of data processing. And to do that, again, we used Azure Machine Learning, because as I mentioned, it can schedule experiments on the cluster, but it doesn't have to be a training experiment. It can be any code which can be automatically parallelized and executed on the cluster. So we use this capability. The next slide, please. So we placed the data set, placed the initial core data set into the Azure Machine Learning data set. And then we created an experiment which will take like every nth entry in the data set, process it through text analytics for health, and then store the output directly in Cosmos DB database, because output is a JSON file. It's the semi-structured kind of form. And the easiest way to store it is in the document database of JSON files. So to do that, what we needed to do, we needed to write the YAML file. If you can go back one slide, I will want to emphasize a little bit like what goes on here. So in this YAML file, you can see we specify like experiment as the grid search. We specify the search space, like what is the space of parameters we want to traverse. And then we say, please run this Python script, use this data set, and use this search parameter. So everything is passed to the Python script as normal command line parameters, and we don't need to worry about like where the data set is. We don't need to know the directory. We just say, I want to take this data set, and HML will do all the magic behind the scenes. It will mount this storage where the data is stored to the container on the cluster. It will run the script, collect the data, and so on. Okay, let's go on. So this is the result that we get after processing the JSON file. And one more. And because it is semi-structured, as I mentioned, we can store it into Cosmos DB database. So Cosmos DB is a NoSQL solution, and you can go on with clicking the slides. And one more. So what we can do, we can formulate queries, and queries are expressed in the language which is similar to SQL. It's not exactly SQL because it queries semi-structured data, not relational data. So for example, here, what I want to do in this query, I want to take all the titles of all the papers which contain medication hydroxychloroquine, and which contains relation dosage of medication. So this query allows me to extract dosages of medications, or the dosages, different dosages of hydroxychloroquine, and papers that then they are mentioned in. So you can imagine if we are specifically want to learn about the different protocols of using hydroxychloroquine, that would be the query we can run and get immediately all the papers of interest. So the next one. What is nice about Cosmos DB is that Cosmos DB also contains built-in Jupyter notebooks, which allow you to take seamlessly data from a result of a query and expose it as the Python data frame. So what we did next to to visualize it, we used Jupyter Notebooks and Cosmos DB. And essentially, you say, this is the SQL query. I want to get the underlying pandas data frame. So we crafted a nice looking query which extracted entities together with ontology IDs. And then we were able to visualize it. And this, for example, shows how different strategies changed over time. And you can see that hydroxychloroquine, the interest in it declined over time. And some other medications like favipiravir were getting more and more popular. And similarly, what we can also do, you can switch to the next one, is to draw relations of different terms. Like this one shows the relation of different treatment strategies and different diseases, and you can compare, for example, how much COVID-19 is different from other types of infections in terms of treatment. And the next one is the relationship between diseases and different specific medications. Overall through all database. And one more is the term co-occurrence, which shows the nice combinations of medicines that were used together. So that is, of course, interesting insights. What we also wanted to do, we want to give people who work with this data set an easy access to that information. And to do that, we used Power BI. So Power BI is the visualization tool. Normally, it's used to build dashboards, but it can also build the interactive exploratory kind of interfaces to work with data. So maybe I can try to show you visually on my computer, and I will zoom in to make it visible. So maybe if we can share my screen for the moment, I will just show what I mean by that. Okay, thank you. So here is the it is zoomed in version of the interface. So we explore different entities. We can click, for example, on dosage of medication here. On, for example, medications, medication name. And on the right, we can see all the medications together with ontology IDs. You can see that, for example, hydroxychloroquine is the most popular one, and HCQ are the same thing because they have the same ontology ID. And similarly, we can explore relations. Like we can go to relations and say, I want to explore dosage of medication. This is the number of usages, and here you have different dosages and their count, how often they appeared in the data set. So this gives a pretty nice overview of what people have been talking about during different periods, and you can further drill down. Like if you click here, you can get the further the list of papers and so on. So I think that's pretty much what I wanted to cover today. Unfortunately, I was not able to show you in more detail like the demonstrations, because I wanted to show like how you can use Cosmos DB interactive querying inside Azure portal, and how the Azure ML tool looks like overall. But yeah, sorry about that. I guess next time we probably should check a little bit earlier to see if everything is working nicely. So the overall takeaways from my talk that I wanted you to take is that text mining for medical text is indeed a really useful thing to deal with large amounts of information, and it can be used in addition to full text search, because like the easiest thing to make anything searchable in the cloud is to use something like Elasticsearch, or we have Azure Search, it is called, and it is pretty intelligent. It can also like extract information from text, but it will not be tied to the domains problem domain semantics. Here, because we use specific tool text analytics for health, we can tie entities to specific ontology IDs. And the next, for example, one thing we can do next is to explore the relations within the ontology. So, for example, the medical ontology specifies like which medicines are of a certain kind. For example, this is the non-steroid type of medicines, and we can, for example, do queries like which papers covered usage of non-steroid medicines to do the treatment. So this idea can be further explored by adding the medical ontology relations. And what is also important from I think to take away from this demo is that you can use cloud tools to build together such a system from simpler building blocks. Like you don't need to invent your own microservice architecture behind the scenes. You know that there is a block which does text processing. You know that there is a block which does data storage in a nice way. You know that there is Azure Machine Learning which can do machine learning and any parallel processing in the cluster. And then you can just put those things together to get the result you want, which can be done pretty easily and pretty fast. And the cloud will take care about scaling. It will take care about like scalability, durability, and so on. So there are good questions that I see whether we have plans to try the model in other languages rather other than English, and that is really good question because no, we don't have plans. But the reason for that is that for a language, to use the different language, you need pre-trained BERT model for that language, and you need to train it on the texts from the problem domain. So we were lucky because we were using the existing service. If we want to switch to different language, we can probably find the BERT for that language, but it would be difficult to find the huge data set of problem domain texts. And the same question applies if we want to switch from medical texts to any other problem domain. We would need to find texts in that problem domain. We would need to have entities somehow marked up. So we need to label the data or find a suitable data set for it. Technically, it's pretty much clear how to do all that. But in terms of efforts, it requires a lot of efforts to prepare the data set. So how much data can Cosmos DB store so that Power BI is still is efficient and doesn't have big loading time? I guess the only way to find out is to try. In our case, what we did, we cached the data on client side, I believe, because like originally we did it in such a way that we did all queries inside Power BI, and those queries, they do not return a lot of information. They return pretty much entities and counts, but most of the processing takes place on the server. So Cosmos DB does the processing and returns back just what you need. So that did not present a lot of problems, but those data that is returned, it's cached on the client side to speed things up. In our case, we did not have any huge problems with the data. But I guess that's definitely a valid question. The thing is that we are not storing papers in Cosmos DB. We are storing just entities and relations, which is significantly less. And we are not processing full texts at this point. We are processing just abstracts. So yeah, we will have the big data issues when we try to switch to full texts. And in terms of graph database, no, we have actually Cosmos DB contains the graph database inside as well, but we did not experiment with that. That's definitely a really good and valid suggestion to convert like entity relationships into the graph format as well. I don't honestly see whether we will get a lot of interesting insights from that. Yeah, but yeah, we need to think about that. Thank you, Alexandru, for this. idea. Okay, any other questions that you might have? I will share. Meanwhile, I will share in the with you the link, because this this text has been published recently on Open Data Science. Let me just find and then towards data science. So let me just find the link where this text can be, this talk can be found as text, in case you want to like look at the code and experiment with it a little bit more.
We have another question about how much annotated data versus unannotated data did you have?
Just a second. Yeah. How much annotated data for NER? So the idea is that we used only annotated data for training, because all the rest was pre-trained by Microsoft Research. So PubMedBert model was trained. First of all, it started with the English language BERT. Then it was fine-tuned on PubMed. And then this BERT model we trained on annotated data. And with annotated data was BC5 CDR dataset. So let me quickly switch to the statistics, because it talks about how much data this dataset has, which is not really a lot. Yeah, 1,500 papers and 5,000 marked up entities. That is for our first experiment. But then for text analytics for health, because it's a service provided by Azure, we don't know what it has been trained on. So we can only guess that it was definitely trained on the well-labeled dataset, because it contains also relations, and it contains a lot of ontology annotations. This is not that is information we don't know, like what it has been trained on.
I also had a question myself. You've spent quite some time looking at this data set, and I was wondering what was the most surprising thing you found out from your analysis, or if there were any surprising things.
Actually, nothing really surprising came up. One interesting thing that we been thinking a lot about is the negation detection, because text analytics for health can also detect the negation when entity is placed in the negative context. And definitely, it was tempting to start, like drawing graphs and saying, look, hydroxychloroquine is mentioned often in the negative context. It's bad medicine. We should not use it. But then we started like looking further how on the examples of this negative context, and it turns out that it's not always negative, and it's just it can say that, for example, I mean, the precise detection of negation is a difficult thing. So I think all this should be only considered from the statistical point of view. Like if you average over large data set, then you can draw some conclusions, but otherwise text analytics is not always very precise. And by the way, looking at the entities themselves, like if we start looking at the extracted entities in this Power BI, for example, they are not always like right. That there are a lot of entities that are not like always perfect. Yeah, so technology right now like works pretty well, but not 100% accurate, which is expectable from AI.
Yeah, that's good to know. So take everything with a grain of salt, but yeah, we're getting there. So this is an important first step in any case.
Yeah. Okay, we don't have any more questions, and I think we are about time. So again, my apologies that I was not able to show you all the demonstrations that I wanted, because a talk without demonstrations is not as excited, as the full one.
Oh, no worries. I think we made it work. So
Somehow.
thank you, Dmitry. It's been
Thank you.
it's been quite interesting. Yeah, and yeah, looking forward to play with this for a bit.
Yeah, if you do, let me know like the results, like if any of our if any of people who watch us have a chance to improve that or play with that. That would be really interesting case for us to know.
Will do.
Yeah, and also like if anyone has any problems with Azure machine learning, definitely get back to me, because one of the things I do as cloud developer advocate at Microsoft is collect product feedback and try to improve the product, and we know that we have some room for improvement. So thank you again for having me.
Thank you.
Thank you as well, Dmitry. No, so it was your cue.
I want to say thanks for allowing us to archive experiments. That's great in AML.
Definitely, and yeah, hope to see you again with a future occasion. Until then, have a great day. And for everyone out there, I think we're going to take a short break. I think we have 8 minutes, and then we resume with the next session.